this is a guess, I think it's around 6, 7, but this is identities. And the first thing I want to do is define what an identity is. So I'm going to write an algebraic identity, and we'll talk about what makes it an identity. So the idea is that I'm claiming these two sides of the equation are equivalent. If we were to give them labels, we'll call this A and we'll call this B. And what I'm saying is if A, then B. And likewise, if B, then A, which you may recall I can summarize by saying A if and only if B. So what does that mean? That means for every possible X I can substitute here that this equality holds. This is different from solving an equation where your goal is to find the X that makes it true. How would we go about that? Well, we could probably start on this side would be best. Let's show if B then A. Well, we would just use, let's start with this. And we just use our rules for dealing with fractions, and we would say, oh, of course, we know this is 2x minus 6. And then we could write, well, 2x is just x plus x. And so we've shown that if B then A. Now, we could just repeat those steps starting with A, but we could also note that all the steps I've taken so far are reversible. So we can simplify this and say, well, the steps are reversible. Therefore, this identity holds. This is proof. And that's what we're going to be doing, although we won't use the word proof. We'll probably say verifying an identity. We want to verify an identity as truth. I'd just like to add one more minor note here, important note. When I say these are equal, or this identity holds, I mean on the domain, right? So if there was an x in the denominator, we would eliminate 0 as part of the domain. Okay, before we start playing with some identities, there's a long list of, basic equivalences, basic identities that you have to have kind of in your toolkit. We've mentioned many of these before, but I'm going to put a few of them up on the board so we can use them. This is kind of, in math, sometimes you start in one place and sometimes you start somewhere else. Here, we're going to call this a definition. By definition, tangent is sine over cosine. We have a definition of sine and cosine, which comes out of you recall out of the unit circle. We have a unit circle. We have some angle theta. And we define the cosine as the coordinates. Cosine and sine are the coordinates of this point that is intersected on the unit circle. All right, so we have tangent of x, cotangent of x is just going to be the reciprocal. Cosecant of x is 1 over the sine, and secant of x is 1 over the cosine. So we have these definitions to work with. All right. So I'm going to do an overly simplistic verification of an identity. Let's show that the tangent of x is equal to 1 over the cotangent of x. So the steps would look like this. We're going to take the tangent of x, and from our definition, we know it's the sine of x over the cosine of x. Using our knowledge of fractions, we know that this is 1 over cosine of x over sine of x. And then finally, from our definition, we know that that's 1 over cotangent of x. So I just have a series of steps where I go from one side of this equation to the other. And again, I'm going to point out that to complete the proof, I need to show if this is true, then this is true, that I can just say, well, the steps are all reversible. Okay, so that's a very simple example. Now, we're going to get some more complicated identities to show. And it turns out that there's one particular identity which is ubiquitous. It shows up almost everywhere. And we might as well get that down. This is called the Pythagorean identity. And you've probably seen it before, but I'm just going to start with our definition of the Pythagorean theorem, which is c squared equals a squared plus b squared, where we have a right triangle where c is the hypotenuse and a and b are the legs. And I'm just going to take a simple step here. I'm going to divide both sides by c squared. So on the left, I get 1. Now, a over c, that's the opposite over hypotenuse. That's the sine. So a squared over c squared is just sine squared. I guess I should give this a label. And likewise, b squared, that's the adjacent over c, is the cosine. So squared is the cosine squared. This is the most common form of the Pythagorean identity. But it's not the only thing we call Pythagorean identity. There's 2 more very common forms you want to be aware of. I guess I'll mark this. We could divide both sides of this by sine squared theta. And then we just want to use our definitions to going to relabel this. This is the cosecant squared. This is 1. And this is the cotangent squared. So this is also the Pythagorean identity. And likewise, if I instead divided by cosine squared, what would I get? I would get secant squared equals 1 plus tangent squared. Next to this first version, this last version is the one you probably see the most. So these three identities, you're going to see are going to show up and assist you. I guess I'm just going to write the main one here. Sine squared theta plus cosine squared theta equals 1. Now these others come up, I'll point them out. What I'm trying to do over here is kind of grow a list of things that should either be in your head, in your notes, your cheat sheet, because any of them may come up again. If you have them in your head, that's the best thing. That way they'll appear at the appropriate moments. Sequence here. And Emma? Yeah. Anybody else sneak in while I'm looking? Okay. There's some very simple but basic identities having to do with oddness and evenness. You may recall that sine of x is an odd function, which means that sine of minus x is equal to minus sine of x. And cosine of x, well, minus cosine of x is cosine of x it being an even function, odd. Memorialize these. Again, these are identities. They're true for every x in their domain. What about tangent? Is that an odd or an even function? Well, tangent of x is sine of x over cosine of x. So tangent of minus x is sine of minus x over cosine of minus x. Sine of minus x is minus sine of x, and cosine of minus x is cosine of x. So we can go back and say tangent of minus x is minus tangent of x. Tangent's an odd function. We can follow the same steps with secant. Secant is 1 over cosine. The cosine is even. So we get that secant of minus x is secant of x. Secant is an even function. Yes?
What's the O and the E next to the sign of x?
Oh. Odd.
Oh, odd.
Sorry. Thank you. And likewise, the cosecant, we'll just skip a step here. It has to be, because it's going over the sine, it has to be an odd function. Okay, so I'm not going to write all those down here. They're pretty easy to derive if you need to on the fly, but they're all going to be useful. Again, before we get to the fun, we have a few more basic functions, a few more basic identities we want to have available. I think this one is best illustrated with a diagram. We have theta, adjacent, opposite, hypotenuse. What do we have here? We have an angle. This is the complementary angle. Which if you know, in your head, if you can rotate this around or switch it, well, why not? Just draw it. It's now the opposite adjacent. Well, we can see some nice obvious identities here. The sine of theta is, of course, opposite over the hypotenuse. I really want to rotate this around and leave these labels. Here we have the cosine of 90 minus theta is equal to opposite over the hypotenuse. Well, it's not the opposite of this angle, but it's the same always here. So immediately you see that cosine of 90 minus theta is equal to the sine of theta. I think when we were doing graphs, we might have looked at that and seen that, sure, if you translate the cosine function, it just overlays the sine function. So I think I'm gonna keep this list going. So we have cosine of 90 degrees minus theta. Leave enough room. Likewise, sine of 90 degrees minus theta, the cosine of theta. I wonder about the tangent. 90 degrees minus theta. Well, now we're actually getting into thinking about how identities can be verified. This is the sine of 90 degrees, 90 degrees minus theta. Cosine of 90 degrees minus theta, which is equal to the cosine of theta over the sine of theta, which is just the cotangent. Okay. As you might expect, cotangent minus theta is the tangent of theta. have the same issue with, say, secant. That's going to be 1 over the cosine of 90 minus theta, which is just 1 over the sine of theta, which will be the cosecant of theta. Okay, I think I'm just gonna leave those off for now. Again, something you can derive quite easily. So these are sometimes called co-function identities. All right. Now we have this nice toolkit here. And so now we can look at some not so obvious, but interesting identities. Let's look at this one. Cotangent of theta plus tangent theta times sine theta is equal to secant of theta. Well, that's not so obvious. So I'm going to give you the first. I'm trying to think of a category. Rule of thumb, strategy. When you see an identity like this, and it's not so obvious what to do with it, a good strategy, starting strategy, is to convert everything to sines and cosines. That's often all you need to do to get through. So the cotangent is the cosine of theta. We're just going to follow this side for now, over the sine of theta, plus tangent. Well, that's sine of theta over cosine of theta. Well, what do we do with fractions? Put them over a common denominator. Yes, thank you. So what do we end up with? Well, our common denominator is sine theta, cosine theta. On top we have cosine squared theta plus sine squared theta. This brings up the second strategy. Look for the Pythagorean identity. As I said, it's ubiquitous. Well, here we have it. Cosine squared plus sine squared. That tells me this is 1 over sine theta, cosine theta. And I've done something wrong. Oh, I left out here. This was sine theta. I hate it when my notes are either wrong or they confuse me.
Wouldn't that mean that the sine squared theta would be
Sine squared plus cosine squared. Pythagorean identity. Can I put that up here?
That's right.
Oh, I must have erased it.
Or it could be that and then times sine.
think I flubbed, but I'm gonna back up a little. See if I can unflub myself here. Well, this is definitely cosine over sine. And this is sine over cosine times sine. Yeah, I'm beginning to think I flubbed something here. Well, this would be a good moment to go the other way, which would be to say, possible that this identity is not an identity. Unlike proving something's an identity, which is, that's why your hand.
Okay, so
Oh, good. All right, go ahead.
I was just thinking, I think you were doing it the right way. It's just, it was supposed to be the Pythagorean, identity, but then you times it by, you leave out one of the sine thetas out of it, and then it would just be 1 times sine theta over cosine theta over sine theta.
I'm going to go with you on this. So this would be sine theta,
It would be sine theta.
cosine theta over
No, it would be,
sine squared theta. No,
no,
no, no, no, no.
it would be cosine squared theta plus sine
Cosine squared theta, yeah, over
plus sine.
theta, cosine theta.
But then it would be also plus sine squared theta over cosine, sine theta cosine theta.
Well, now I need sine cubed, don't I?
I think you're doing the sine too early is what she's saying, like you leave that
Do you leave the sine out?
after you have
Would you do me the honors?
I don't know if this is right, this is what I was thinking.
That's okay. We learn by our
So
mistakes.
it would just be the thing where you did cosine squared theta. And sine theta over
Okay, so where I'm mixed up is, okay, cosine squared over cosine over sine would be,
Oh, wait, sorry.
would be cosine over sine, which is right. But, but it's also times sine.
So then you would just, you would leave this one out instead. So
I can, it's not there. I think it's just wrong. So we're gonna take a totally different direction, even though it's the wrong time to do it, which is to say, I wonder if I could have gotten this wrong. Let's try some value, see if it works out. So how about, I'm just gonna pick pi over 4, because I think it'll be useful. So cotangent of theta is cosine theta over cosine of pi over 4 sine pi over 4 plus tangent, which will be sine pi over 4 cosine pi over 4 times sine pi over 4. And we want to show that's equal to the secant, which is 1 over cosine of pi over 4. I hope I didn't choose the wrong value. It's just going to come out anyway. But this is 1 over the square root of 2 over 1 over the square root of 2. So 1 plus 1 times 2 equals square root of 2. Ah! My example has a typo. Well, I've shown that it's not an identity, so oh, look at that. I've rewritten it properly. Dang. I must have typed it in wrong. Let's see. So, yeah, my notes have failed me badly here, I can see. Why is that? Why is that? Well, okay. I don't want to waste your valuable time. Let's try something else. We're going to be doing these for a couple of days, so I can come back and find out where I went wrong. Okay, so the proposition here is cosine theta times secant theta minus cosine theta equals sine squared theta. All right, let's give this a try. Again, I'm going to use that strategy of switch everything to sines and cosines. That often makes things more apparent. Theta secant is 1 over cosine theta minus cosine theta equals, well, we're just going to leave that off. We're going to follow this down. Multiplying through, I get 1 minus cosine squared theta. Can anyone see where that goes immediately? Sine squared theta plus cosine squared theta is equal to 1. And 1 minus cosine squared theta equals sine squared theta. So this just immediately becomes sine squared theta. Now, we've taken it in one direction, but all these steps are reversible. So we verified this identity. We're going to do a few identities in a few minutes that you'll go, oh, that's obviously useful. But in the homework, you're going to see a lot of these. They're like little puzzles, show this. And you might scratch your head and say, why are we doing this? This is a skill that we're going to try and teach you just like factoring FOIL. And there's no obvious reason in this class. However, what you're going to find in the next class, the calculus class, when you take that, is that in calculus we do a lot of work with trigonometric functions in which this is exactly the skill you're going to need to complete what you're doing. You're going to find some problem, you're going to manipulate things, and all of a sudden you're going to have this, and you're going to want this. And that's why we're learning this skill. So, all right, so let's take another kind of typical obscure looking identity. 2 times the tangent of x minus the secant of x is 1 over 1 minus sine of x times 1 over 1 plus sine of x. Well, as before, put everything in terms of sines and cosines.
Is that times or minus? Because you said minus, but like is it?
Oh,
But also
oh, ouch,
in,
ouch.
for the other side too.
Now my hand is disconnected from my mouth.
Yeah, but for the,
Sometimes my hand is disconnected from what I'm seeing.
for
No.
the front part, you said.
No, this is multiplication, this is subtraction. I'm sorry. Got that? All right, so let's convert this. Well, good. We can go either way. We can work this and try and get this. We can work this and try and get this. Sometimes you have to try both of them and find the one that's going to get you there. And keep these theta. We're going to follow this side down. Somehow it looks like it might be simpler. So again, we're going to put these over a common denominator. I'm just going to swing this over here. So I'm going to get 1 plus sine of theta minus 1 minus sine of theta over 1 minus sine theta times 1 plus sine of theta. And we carry this minus through. This is minus 1 plus sine. So on top, we have
Just basically like, yeah, you did it and then reordered it, so that makes sense.
That's the same one.
Yeah.
It sounds too low.
How many?
Yeah.
And this one, sir?
Yeah. Because it's like, yeah.
I'm surprised I even passed. Yeah, because I was still
I like this building.
So students want to say that.
Because like, I don't want to take
Well, it's basically, yeah.
that sucks.
But basically, like if you look at the call, it doesn't, like, it's the same, like, it's for the lines. So you need to have one for yeah, and you need one from a higher level, so you have to handle it and then start classes to get to that, like, to, did you do, I just finished one.
Eight, no, I was Spanish. You don't get credit for SLs. This is a really good credit for detail. It's depressing. I want to take Spanish. Wait, I'm looking to take Spanish this year. I mean, this semester. I don't want to take. I don't want to take Spanish. I don't want to take any Spanish in high school. I was like, I'm so scared. I could also just take, I forgot, for like, I was listening to the person. I didn't want to take the person because I just didn't want to take Spanish. I forgot. I was really bad. Language is like my kids. I've never
Do you have any pianists in here? Anyone who plays piano?
It just counts as an elective. Like, pre-req class that counts as being.
No way.
No way?
I took lessons for 7 years until like middle school. And I had this really strict teacher. It was like, it was hell.
Did your teacher get you?
Oh no, but it was like strict in that like,
Verbal abuse?
no. It was like, it was just like, in terms of like how I should study. Like, if I messed up, like, she made me not the ideal teacher you want as like a middle schooler.
There you go. I played trumpet in middle school, and we had a band director who like, well, I can say this here, it's a Catholic university. He put the fear of God in here, you know. But I was no good at trumpet either after 7 years. Nobody really told me that there's one important thing you have to do when learning a musical instrument. Can't hear you.
Consistency?
No, you have to practice. You have to practice. I didn't know that. But I bring up piano because I was like, if you were a pianist and all of a sudden, one day, one of your fingers was like pressing the wrong key all the time. It's like, you want to play D, but it plays C. And you kind of go, oh gosh, maybe I have to get a new job. I say that because I'm having that with typing. I type things, and then sometimes one of my fingers types the wrong key.
He tried to, there's like, I guess this is what I used to kind of do.
I've been doing it for 50 years. I'm pretty good at it. Mostly I learned it when I was I learned it in high school, but I didn't really. I learned where the fingers go. But when I got into programming, you know, it was just like after a while, you know where the weird characters are too. But now it's failing me sometimes, which is to say, not to beat a dead horse, but now I know where I went wrong on that first example. See, I wrote cotangent theta equals plus tangent theta sine theta equals secant theta. And there we go, cosine. The similarity between computer programming and math, it just needs one letter wrong. All right, we can do this quickly now. Cosine theta plus sine theta over cosine theta times sine theta. Okay, let's put it over common denominator. Cosine squared theta sine squared theta over cosine theta. Skip a step, but you can probably see how that is. Cosine squared, well, that's just 1 over cosine theta, which of course is the secant of theta. That's a simple problem. I messed this with that. But, you know, there's some words of wisdom there, which is, you know, something's not turning out right, go back, look it over, try it again, be more careful, try it a different way. That's not only helpful in math, it's helpful in many, many phases of life. Of course, not if you're an airline pilot. You want to nail that landing. Okay. We're gonna talk about some additional identities that are not just kind of arbitrary and, oh, you know, I think I want to try something different. I just want to point something out. Take a minute for this to warm up. But if you ever find yourself in a place where you're thinking, is that really an identity? It's kind of a technological cheat you can do that will give you a little confidence in what's going on. I'm going to use Desmos, but you could use your calculator on your TI calculator. Online. I'll show you an example here. You might as well just take that example you just did. Hurry up. Oh, didn't even type that in. All right, so let me do it the wrong way first. Cotangent, Desmos likes x's plus tangent sine. Okay, that was the left side of the equation. The right side was secant. clearly I did something wrong because these do not match. Let's see what happens if I replace this with cosine. Uh-huh. This is what you should see. This is kind of a cheat, but it's nice. It's a nice little graphical view of things. If you have an identity and you graph one side or the other, they should overlap. They should be the same. This one's so simple that worth 60 seconds. I wonder what sine of minus x is. Could it be sine of x? No. Minus sine of x, right? So this is just, kind of like first grade if they gave you some blocks to learn how to add or multiply. This is kind of the high-end college version of it. All right, I wanted to show you that. It's a nice modern way to kind of check up on yourself. Leave this here for the moment. All right, so as I said, there are some really useful identities that we need to put over here. You need in your head, or on your cheat sheet, or in your notes. We're going to start with this one. Cosine of x plus y. This comes under the heading in addition formula. This is going to be one of the few identities where we're going to actually fall back on some geometry to see what the result is. You don't have to reproduce the geometry proof, but it's straightforward enough that I think it's worth taking a look at. What we want is a description of cosine of x and y in terms of some trig functions in x and or y. So the way we do this, we start with a unit circle. And we pick an arbitrary point in the first quadrant, which we're going to call P. And we're going to give a name to the measure of its sector here. We're going to call that R1, which, if you remember from your geometry, means that this angle here will be R1. We're going to fill in the coordinates in a minute, but we're also going to give this point here A coordinates 1, 0, right? Right. Next, we're going to pick an arbitrary point in the second quadrant. We're going to call Q. And again, we're going to describe the length of the sector from PQ to be R2, meaning this angle is R2. So we would write that sector equals R2. So we could say EA R1. And finally, we're going to pick a third point in the fourth quadrant here, which peculiar reasons, we're going to call it R. But this is not an arbitrary point. This is a point such that AR is also equal to R2. I guess that's a good reason. So now, we want to start labeling the coordinates of these points. Well, P is going to have the coordinates cosine of R1, sine of R1. Q is going to have the coordinates, since its angle is R1 plus R2, cosine of R1 plus R2, sine of R1 plus R2, and finally R, well, this is, the angle is negative R2. So this is the cosine of negative R2, sine of negative R2. Okay, so that's the geometry setup. We've got a circle. We have some points on the circle, and we know the coordinates. Now, if we draw the lines QA and PR, well, they intersect at an angle of R1 plus R2, as does this segment, this segment. So since these arcs are the same, from geometry we know the length of these two lines is going to be the same. So what we're going to do to get this formula is we're going to equate the lengths of these two lines. How are we going to find the lengths of the lines? Well, we're going to use the distance formula on the coordinates. So, this is where the fun begins, I guess. So we know QA equals RP. Okay. I think I'm going to run out of room here, but I'll do my best. So, from QA, we're going to use the distance formula, square root of cosine R1 plus R2. Oh, the x coordinate is 1. Plus sine of R1 plus R2 minus 0 squared. Okay, that's one of the lines. PR, well, that's going to be square root of cosine R1 minus cosine negative R1 squared plus sine of R1 minus sine of negative R1 squared. So this distance is this square root. This distance is this square root. So now I'm going to do some graphical cheating. I'm going to square both sides, and I'm not going to write it again. I'm just going to erase the square root signs. All right. So what do I have here? I have cosine squared r1 plus r2 minus 2 cosine r1 plus r2 plus 1 plus sine squared r1 plus r2 equals, and then from this line, it's going to be cosine squared r1 minus 2 cosine r1 cosine r2 plus cosine squared wait a minute. Negative r1 cosine squared negative r1. That's this first part. And then we have sine squared r1 plus 2 sine plus 2 sine r1 sine of negative r1 plus sine squared negative r1. Oh. Fortunately, it's time to erase this. Okay, so let's look ahead here and see where we might save ourselves some trouble. I've got cosine minus r1. Did I write down the, there it is, cosine of negative x. Wait a minute. That's been on the board. How many minutes? No one saw it? So this is just cosine of r1, or 2 cosine squared r1. Simplify that. Sine of negative r1. Negative sine r1. So that's just sine squared r1. Goes here. So you've got cosine squared plus cosine squared minus 2 cosines. Hope I got that right. Uh-oh, it doesn't look right. That's why I left some additional notes to be on track here. back and look at my diagram, because I think I wrote something down wrong. Oh, well, first of all, I left out some R2s here. Heavens. So this has got to be R2, so my simplification is just wishful thinking. All right, now we can get this back on track. So, cosine R1, cosine negative R2 would be just cosine R2, minus I'm just having a terrible time with FOIL here. Oh, cosine squared R1 minus cosine R1 cosine R2 plus cosine squared negative R2. That's the first line. Plus sine R1 squared plus 2 sine R1 sine negative R2 plus sine negative R2 squared. Okay. Cosine squared R1 plus sine squared R1. Sine squared plus cosine squared is 1. Cosine squared negative R2, sine squared negative R2 is also 1. Cosine squared R1 plus R2, sine squared R1 plus R2, that's 1. So let's write what we have left. 1 plus 2 cosine R1 plus R2 plus 1 equals, well, I've got these two ones here. Now, what do I have here? Cosine R1 and cosine negative R2, but I can ignore that minus because cosine is even. So minus cosine R1 cosine R2. Here, I can't ignore the minus. Sine of minus R2 is minus sine of R2. So that's plus, I left out the 2 here, didn't I? Plus 2 sine R1 sine R2. Okay, 1 plus 1 is 2, And we have 2 on this side. This was a minus. So we divide through by -2, and what do we have? Cosine of R1 plus R2 equals cosine R1 cosine R2 minus sine R1 sine R2.
Would it be negative on the other side? If you're dividing by
I'm dividing by -2, so I get rid of the minus and the 2. I get rid of this -2, and I divide by -2, so this becomes minus. That's it. Cosine of x plus y is cosine x cosine y minus sine x sine y. Ah. Should you never have to do this in front of class? All right. I'll wait. It's on the video too, if you need to go. That's the big one in this class. That's the most algebra torture I'll push you through. You need me to put something back?
Sorry?
You need me to put this back? Or you
I
just
don't
want-
see it.
Okay. All right. So, okay. So from here, things get easier. Extremely important identity. This is the addition formula, but what about the subtraction formula? Well, that's just going to be cosine x cosine minus y minus sine x sine minus y. But from our odd even identities, you can see this is just cosine x cosine y plus sine x sine y. In other words, the negative y here, well, it's just the same as y. The negative here gives you a minus, so this becomes plus. So sometimes we'll write this more simply as x plus or minus y is minus plus. So we can simplify that a little. I'm just going to erase these. Okay, so two really important formulas. Well, the obvious question then is, what about sine x plus y? Well, maybe we can save a little effort. You remember the co-function give that a try. We already know what this is, right? That's going to be cosine of 90 degrees, cosine of x plus y, plus sine of 90 degrees, sine of x plus y. Cosine of 90 degrees is so we can forget this. Sine of 90 degrees is, oh, that didn't help. We knew that. Why did I go down that path? Oh, well, okay. Glad we got the right one out of it, but. Going down a slightly different path. This is cosine of 90 degrees minus x minus y. Maybe that'll work out better. All right. Cosine of 90 degrees minus x times cosine of y plus, because this is minus, sine of 90 degrees minus x sine of y. Okay, much better. But what's the cosine of 90 degrees minus x? That's co-function identity. That's just the sine of x. And what's the sine of 90 degrees minus x? Should be popping right into your head at this point. Cosine of x. Aha! So now we know what the sine of x plus y is. Might as well write that in. These both have kind of a nice rhythm to them. They're different. Cosine of x plus y, cosine x, cosine y minus sine x, sine y. Sine of x plus y is sine x, sine y, plus cosine x, cosine cosine y, cosine x, sine y. And if we want to add the plus or minus here, where are we going to end up with? It's minus y stays the same, it's going to change, so it's going to be plus or minus. From here it gets easier. What's the tangent of x plus y? It's going to be the sine of x plus y, cosine of x plus y. These are things I don't think, actually, these two are good to memorize because then you can pattern recognize them. Not so much the tangent, not this semester anyway. But you should jot these down, for reference. Okay, sine x, cosine y, plus cosine x, sine y, over cosine x, cosine y minus sine x sine y. Okay. But we would like to have that in terms of tangents. So let's multiply that by 1 over cosine x cosine y over 1 over cosine x cosine y. So what's that going to do for me? Sine x cosine y over cosine x cosine y. The cosine y will drop out. We'll have sine x over cosine x, which is tangent x. What do I want to do? Cosine x sine y over cosine x cosine y. Okay, now the cosine x's drop out, sine y over, right? Tangent y. Did I do that too fast? This over this is tangent of x, this over this is tangent y. Cosine x cosine y over cosine x cosine y, that's 1. Minus. And then we have sine x sine y over cosine x cosine y. That's tangent x, tangent y. So that's our tangent addition formula. And, similarly, put a minus here, what's going to happen? It's going to become a plus.